discussion today. Now, we said yesterday that matter is made up of tiny particles. At times we call them atoms. There are also some different types of matter can exist as atoms, others can exist as molecules, and others as ions, right? Now, what happens when the state of matter, irrespective of whether it is a gas, a liquid, or a solid, when it is either heated or cooled? That is what we want to discuss today. And we shall be using water as our reference, because water is everywhere. Everybody knows about water, its properties, and also its state, or its states in under different conditions. So that's why I have picked on water, so that everybody is comfortable. Right now, the simple question: when let me just matter. What exactly? What? Say it again. I can't hear you. I think your network is bad. I can't hear you.
About the what?
Your network is bad, so you better mute yourself so that we can continue, because I can't hear what you are saying. Right. I was saying that what happens when matter is heated. Let me start from the heating part of it. Then we shall look at the cooling part later. So when matter is heated, what exactly happens? Now, I was saying that we are usually we know that matter is made up of particles. I don't know why some people are putting up their hands. I can put it up. What is the problem?
Excuse me.
Akamprira, can you say what you want to say?
I want to give you the answer.
No, I don't expect the answer. Thank you, but I don't expect the answer right now. Just listen, and then if I want you to answer, I will pause for some time, then I will let you give the question, the answer. But this one, I'm just bringing it as a starting point. Now, we said matter is made up of particles, tiny particles, and which we call either atoms or molecules or ions. And those particles are too tiny, so tiny that you cannot see them with your unaided eye. Okay. For example, even if you have perfect vision, you cannot. If I told you to give me or to show me one molecule of water, it is impossible. There's no way you can isolate or identify one molecule of water. And if I said give me one atom of oxygen, it will be next to impossible, because those particles are very tiny. Okay, it is only when they are in large numbers that we can see that this is either copper, or this is common salt, or this is water. Okay, so when you hit these particles, what exactly happens is what we want to discuss. Now, when you hit a substance, it means that the particles of that substance are going to take in the heat energy that you are giving them. For instance, if I'm heating water, it means the water is going to gain the heat energy that I am supplying. Possibly I'm using a Bunsen burner or I'm using a charcoal stove. So the charcoal stove is the one supplying the heat to the water. Now, when that water gets, when the particles in the water get that energy, what happens to them?
Evaporate.
What? Not really. Not really. Before that, what happens is that
Expands.
not to give answers as yet. What happens is that the particles, when they gain that energy, they become more active, if I can put it in a simple language. Okay. Now, in science or in chemistry, we say they gain kinetic energy. And if they gain kinetic energy, it means they move faster. Okay. So in other words, because when we looked at the other pictures yesterday, we said that the picture which was showing the people who were arranged such that they were too close together, the picture that was in the middle of the three, the human beings were too close together and movement was almost not there. So the movement can be restricted into vibrations within mean fixed positions. However, in liquids, the movement was to some extent possible. The movement of the people, they could move, though the picture was just a still picture, so you cannot see them moving. But just consider yourself in a class. Let's say your classroom, you are about, let's say 10 of you in the class. That one could be representing a gas, the gaseous particles. So when you are only 10, movement within that class can be very, very easy. And that's how the gas particles are. Their particles can move very easily because they have large spaces between them. Now, when it comes to liquids, the movement will be there, but not as much as what we saw in gases. And when it comes to solids, the movement is restricted to just vibrations. Yeah. So now when we look at water, for example, because that is our point of discussion today, we want to see what happens when the water is heated or when it is cooled. So basically, we have said when you supply the heat to the water, the particles in the water are going to absorb that heat. Okay. When they absorb heat, what happens? Now you can imagine when you are hungry. Let's say you have not taken food since morning up to evening time, right? And then somebody gives, a good Samaritan gives you the food in the evening when you have stayed the whole day without eating. One is that during the day when you don't have when you have not eaten anything, you will not have the energy. But after you have eaten what you have been given, you gain energy. You become energetic because we get the energy from what we eat. Okay. So similarly, these particles in water, when they gain that heat energy, or the kinetic energy for that matter, because they will gain heat, the temperature increases, and therefore they move faster. Okay, why do they move faster? Because they have now gained the energy. Okay? So they tend to move faster. On the other hand, if we try to cool those molecules down, or those particles, if we cool them down, it means we are removing the energy from them, and therefore their movement will also decrease because their kinetic energy will have reduced. Okay? Now let's see what happens to water. We want to begin from water when it is in the solid state, which we commonly call ice. Okay? If you have ice, just share with you is simple, just one minute, and then I will put it off. I'll just share for one minute, then I'll put it off. Now, when you look at this diagram, this animation, I want you to take note of what is going to happen when I have the ice cubes in a beaker. So just see what happens as there will be a thermometer besides the animation and also the ice cubes in the beaker being heated. So just for 1 minute.
According to the kinetic theory, the average kinetic energy of particles increases with the increase of temperature.
Right. I hope you watched the particles on the left-hand side, the blue particles. Okay. As the Bunsen burner was hitting the ice was melting. But at the same time, on the left-hand side, you saw the particles. If you watched very carefully, you see the particles begin slowly, then they move faster. Okay, and then on the right-hand side, you are seeing where the thread of mercury in the thermometer was shooting up. It was increasing as these particles are heated, we gain energy, and therefore that makes them move faster. Okay. Now, we know that the properties of ice and the properties of water are not exactly the same. A piece of ice, when you touch it, in most cases you feel as if it will be slippery. If you touch a piece of ice, for example, when it has rained hailstones, when we were young, we used to pick those hailstones, and then we okay. Now picking them is quite difficult because they are slippery. As you try to pick, they are slippery. But when you look at water, even if you dip your hand in water and you possibly did that, there will be nothing to show that it is slippery. Okay? But with the ice, when you pick a piece of ice and it is slippery. Okay, so the properties of the different states may not be exactly the same, just as I'm saying that the properties of water and the properties of ice will be slightly different. Though we know and we are aware that water is made up of atoms of hydrogen and oxygen chemically combined together. So when we are cooling ice, those are particles. Okay? So they have the same composition, but the structure of matter, let's say we change from ice to water in the liquid state, the structure of the arrangement of the particles that make up that ice or that water will change. At the same, ice is slippery. When you look at the properties of ice, they will be different from that of water. So they will not have the same structure and the same properties. Now, I want us to begin from the point of view when you have ice. Let's assume that I know it is supposed to be an activity but I don't expect you to have thermometers which can read up to or from negative, let's say 5 degrees centigrade up to about 150. You don't have those gadgets at home, but we shall just discuss it. And the activity which I will give at the end will be done theoretically, because I will have explained what I will want to explain. Now, when you have ice cubes in a beaker, and then you put a thermometer inside the ice cubes, and you start heating them either using a stove or a Bunsen burner or any other source of heat. What is going to happen is that as you heat the ice, the temperature is going to, if the ice was at a temperature which is, let's say, at -5, as I said much earlier, that ice is going to increase in temperature. You'll be seeing the mercury thread of the thermometer rising. So it will increase until when it reaches 0 degrees centigrade. And when it reaches 0, it is going to, the thermometer is going to stop, the thread is going to stop rising. We shall explain why. It will stop rising until all the ice has melted. That is when it will start increasing again. So you start with ice at -5 degrees centigrade, for example. When you watch the mercury thread, you'll see it rising as you heat. However, when you reach 0 degrees centigrade, even when you are continuing to heat, the temperature will show, or the thermometer will show, no rise in temperature. You will see the mercury thread remaining the same, but the heat is being supplied by the Bunsen burner. But the mercury thread will not be moving. Then when you continue heating, when all the ice has now melted into water, when you continue heating, as you heat, you'll be able to see a rise in the level of the mercury thread in the thermometer. You'll see it rise. Now it will rise until it reaches about 100 degrees centigrade. Of course, in most cases, it may not be exactly 100. I'm using 100 as an average temperature at which water boils. But definitely we know that water may not necessarily boil at about 100. Because if you try it like in Nasimolo here, in Nasimolo Girls School, when you heat the water in the lab, it will only boil at a temperature of about 96, 97. But it will not reach 100. And we know very well that the boiling point, of course, depends on the altitude. That's why there's that difference. But if you went to a place like Mombasa, which is at a lower altitude compared to Kampala, the water will boil at a higher temperature than 96 degrees centigrade, as it is in Nasimolo. So that difference is caused by the change in the altitude and therefore the change in atmospheric pressure. So when you heat and it reaches about 100, that's why I'm saying about 100, because it may not reach exactly 100. So when it reaches about 100 degrees centigrade, the mercury thread in the thermometer will also again stop rising. You will see it stationary for some time. It will boil, it will, as it starts to boil, it will remain at about 100 degrees centigrade. And then eventually, if all the water has turned into steam, if we check the temperature of that steam, you will be able to find that the temperature keeps on rising, that of the steam keeps on rising beyond 100. So now, what explanation can we give to the fact that when you have the ice cubes in a beaker and you start heating them, the temperature, when it reaches 0 degrees centigrade, it does not increase until all the ice has melted. Now, the explanation is that the heat that you are adding onto the ice at 0 degrees centigrade, that heat does not raise the temperature of that ice, or that ice which is turning into water. It doesn't raise the temperature. But what does it do? Because you can see that the heat is being supplied, but the temperature is constant at 0. Now, where does that heat go? Now, that heat that you are supplying, instead of increasing the temperature of the water, or increasing the temperature of the ice which is turning into the water, it will be used to break the forces that are holding the molecules of water in ice. Okay. So those forces will be broken. So as you break those forces, the ice will turn into a liquid water. So now, because we are supplying heat, but that heat is not manifested in the increase in temperature on the thermometer, so we say that heat is hidden. We call it hidden heat. Now, in science, they gave it a name. They call it latent heat. Latent is a Latin word meaning hidden. It's hidden heat. Now, because it is melting, we give it a name of latent heat of fusion. Okay? When the ice is melting, that we say the ice is fusing. When we talk of a fused substance, that means a substance which has become molten due to heating. For example, if I have sodium chloride, sodium chloride is common salt. We can heat it until it becomes liquid. We say it has melted. When it turns from solid to liquid, we say it has melted. So the liquid sodium chloride will be molten. So in the same way, if you have ice and you heat it, it will turn into water, which is a liquid. So that process, we call it melting, but we can also refer to it as fusing or fusion. So that heat, which is supplied to but is not changing the temperature of the ice, is what we refer to as latent heat of fusion. Now, that temperature will remain at 0 as long as we are as long as the ice particles or the ice cubes are still there. But when all the ice,
Your network is breaking.
My network is check your network.
Is saying it's teacher's network. It's not his.
Keep quiet.
There are some.
Keep quiet.
Very many of you are talking.
Excuse me, teacher. Yes, teacher.
What I'm going to do, I'm going to mute everybody, I think, because we are misusing the chance. When you are talking at the same time I'm talking, it means the network definitely will be affected. you will not be able to listen and hear what I'm saying. And at the same time, I want to request that, you see, you cannot serve two masters at the same time. I see people throwing chats or putting chats in the chat room. How do you write at the same time you are listening to what I'm saying? Because next time what we shall do, we shall block the chats, and then we also block the mics so that you cannot talk and you cannot chat, but listen. Yes. And you see, what you are putting in the chats is nothing related to what we are discussing. So I want to request that you stop the chatting, which is not related to what we are doing, or else I'm going to block you completely. Right. So we have seen that when you hit the ice and the temperature reaches 0 degrees centigrade, that ice, that the thermometer will not register any increase in temperature until all the ice has melted. That is when it will register temperature, the temperature change or increase in temperature. Now, after 0 degrees centigrade, what happens? When you see that all the ice has been removed or has been turned into liquid water, when you reach 0 degrees centigrade, now when you supply more heat to that water, because now it has turned from ice to water, when you supply heat, the heat is going to raise the temperature of that water, which will be manifested in the rise of the level of the mercury thread. Yeah. So that will go on and go, will continue until the temperature reaches about 100. That means the heat that you are supplying to that water is not turning the water into something else, but it is increasing the temperature of that water. Unlike that, the earlier case where we was applying the heat to the ice, but when it reaches 0 degrees centigrade, it stops rising. The thermometer thread stops rising until all the ice has melted. So I will be showing you a diagram. For example, this one which I've drawn. We begin from point A. Point A is representing ice, which is at about minus 25 degrees centigrade. That is point A. At point A, we have ice at minus 25 degrees centigrade. Now, when you supply heat to that ice, what happens? The temperature of the ice will continue rising. The ice will warm up. And it will warm up. As it warms up, the temperature goes on increasing from minus 25, minus 24, minus 23, minus 10, until it reaches 0. Okay. So the heat that we are giving that ice will be the heat that is changing the temperature of this ice from minus 25 to 0. So we can actually see that the amount of heat that we are giving the ice is doing something, is increasing the temperature of the ice up to 0. But now, when it reaches 0 degrees centigrade, it remains constant. The temperature remains constant at 0. That is between point B and C. You can see that the temperature is not increasing. It remains constant. That means that the amount of heat that you are supplying to the ice is not being used to raise the temperature of the ice, but it is being used to break the forces that are holding the molecules in the ice so that they turn to water. That is why the temperature remains constant. Then when all the ice has melted at this point here, when all the ice has melted, as you continue heating, the temperature increases. That means the amount of heat that you are giving to that water, it is used to increase the temperature of the water until it reaches about 100 degrees centigrade. Now, when it reaches 100 degrees centigrade, the temperature remains constant again, as you can see. It remains constant, it doesn't increase. So at this point, the water starts boiling. So as it starts boiling, the temperature will remain at 100 degrees centigrade, which is the boiling point, which is about the boiling point of water, until all the water has boiled off. Because as you boil water, the liquid molecules turn into steam. So that means that point E, all the water has turned into steam. And therefore, between E and F, you have only steam. And between E and F, you can see that as you supply the heat, more heat to that steam, it is used to raise the temperature of the steam. Okay, so we are starting from point A where there is ice. So between A and B, we have the solid state only. Water is in the solid state, that is in form of ice. Then between B and C, the ice is turning into liquid water. So that the amount of heat which you are supplying is not used to raise the temperature of the ice, but it is used to break the forces that are holding the molecules of water in ice. So until all the ice has melted at C, that is when the temperature begins to increase. So in other words, we can say that between A and B, we have the solid state only. Then between B and C, we have both the solid state and liquid state coexisting, because you have some ice will be present and some water will be present, since the ice is turning into the water. Then at point C, when all the ice has turned into liquid water, as you supply more heat, that heat will be used to increase the temperature of the water from 0 up to 100. Then when you reach 100 degrees centigrade, the water begins to boil. As it boils, the temperature remains constant. Because usually, even in our homes, when we are boiling water, if you take the trouble to take the temperature of that boiling water, once it starts boiling, the temperature will remain at that temperature of the boiling point, which is about 100. But as I say, there are cases when you can have temperatures which are slightly less than that. Okay, so that is because there are places which are at lower altitudes where the temperature at boiling point is higher, and there are places at higher altitudes where the boiling point is lower. For example, if you watch the news on TV, at one time they showed water boiling at the top of, I think it was one of the mountains in the west. There was water boiling, but there was no fire. Okay? That means that at the top of the mountain, the atmospheric pressure is reduced. Okay? It is reduced so much that it takes a very short time for the water to start boiling, and therefore its vapor pressure will be equivalent to that atmospheric pressure. Because if anything is to boil, it means that the saturated vapor pressure, because as you heat, the vapor rises or goes up, or the molecules of the liquid turn into vapor. So there will come to a point when the vapor becomes saturated with those molecules. Okay? And at that moment, when you check the atmospheric pressure, it will be the same as the pressure of the vapor, the liquid that we are boiling. So that point or that temperature is what we call the boiling point of water, or the boiling point of the substance that you are heating. So in other words, the boiling point is the temperature at which the saturated vapor pressure is equal to the atmosphere. So in places where you see water boiling, when there is no fire, it means the vapor pressure, the atmospheric pressure is so low indeed, such that even the sunshine can be enough to make the saturated vapor pressure be equal to the atmospheric pressure. Therefore, boiling occurs when there's no fire. So at one time, we saw people putting their eggs in that water that was bubbling, and they were getting water. Okay. So that is it. Now, so it means that if I this is the heating valve for water, because we are starting with ice and we are heating it, and the water is increasing. I mean, the temperature is increasing. So when at the end of the call, I'm going to test. You also draw a cooling curve for water. This one is a heating curve. You are heating the ice until you get the steam. Okay. Now I want you to, in your notebook, to draw. Of course, I'll be expecting you to have to start with this one here. It is there in your workbooks. And then you also draw a cooling curve for water. That means you will start from the steam until you get the ice. Here we started with the ice until we got the steam. But in the cooling curve, we start with the steam, it is very hot, and we shall end up with the ice, which is very cold. So the vertical axis will have the same parameters. It will have temperature in degrees centigrade. And then the horizontal axis can be the time in minutes. Okay. However, you may find that when you are boiling different amounts of water, it will not take the same time. If I have only the 1 liter of water which I'm using or which I'm boiling, it may not take it may not take a whole 1 minute before it boils. Also, depending on the amount of heat that I'm supplying to it. But if you are heating the whole jerrycan, 20 liters of water, it will require some bit of time, which may be more than 1 minute. Okay. So the amount of time taken for the ice to turn to water and the water to turn to steam, it is relative. It depends on, one, the amount of heat that you are using, and also the amount of solid or the ice that you are heating. Okay. So on this axis, you can leave the temperature as the way it is, and you imagine you are now cooling the steam. So how is your graph going to look like? That is what I'll be looking for when I'm checking your notebooks, or when we are checking your notebook. So this is the cooling curve. I want you to draw it in your books, and then you also draw. I mean, this is the heating curve. I want you to draw it in your notebooks, and then you also draw the cooling curve for the same substance. This is water we are talking of. A heating curve for water. Then you also draw a cooling curve for the water. That means you start with steam, and then you end up with ice. But in the heating curve, we started with ice, and then we ended up with steam. I'll just give 1 minute to people who ask, but I want you to be disciplined so that when you are asking, ask questions which are relevant. Questions which are relevant. So I'll start with the Razia. Razia, Lynn. Okay, Lynn. Razia seems to be taking a bit of time.
Excuse me, teacher.
Yeah.
I was asking if steps between.
You have a sound in the background which is making it difficult for me to hear what you are asking. Or there could be somebody who is it? I think it is Razia who.
Teacher, I was asking if.
Yes.
I was asking if there are names given to the states between steam and water and the ice, between the ice and the steam.
Let me first ask people to unmute. If you have if we have allowed one person to talk, yes, should unmute. Should mute your mic so that we don't have the interruption. I'm receiving sounds which are interrupting the person who is asking, and I cannot hear what she is asking.
Excuse me, teacher. The person who's bringing feedback is Amal Bushra. She's the one who's bringing back feedback. Amal.
Can we ask Amal to unmute? To mute your mic, please, Amal. Thank you. Okay, Lynn, you can continue.
Teacher, can you please tell Lynn to mute herself?
No, Lynn is the one who is asking. I thought it was Lynn who was asking.
Yes, teacher, it's me who's asking the question.
That is Lynn, eh?
Yes.
Yes, proceed.
Teacher, I was asking if between ice and the steam, if in between there's any other name given to the liquid.
Is there any other
name given to the liquids during the melting of the ice?
Can you suggest the name that you are referring to?
I don't know, that's why I'm asking.
Now, why do you ask what is not there? Because we have ice, which is the solid state. We have water, which is the liquid state, and we have steam, which is the the gaseous state. Now, I don't know why you are interested in adding another state in the three states which I have mentioned, because we have not yet talked about the plasma in as far as water is concerned. We are just talking about ice, water, and steam, and we are stopping there. So even the diagram that I have requested you to draw, you are only limiting yourselves or ourselves to those three: ice, water, steam. Don't go beyond, because under normal conditions, it is not possible for us to get the plasma if you have the water molecules turning into liquid, I mean steam, and then you get the plasma, we cannot be able to do it. So I hope that is.
Thank you, teacher.
And then
Excuse me, teacher.
who is that? Who is that? Mention your name and then you ask. You have disappeared.
Excuse me, teacher.
Yes, why mention
Excuse
your
me,
name
teacher.
and then you ask the question that you want to ask.
I'm Ankunda Rolita. I just want to have one more look at the curve card for water.
The curve that the heating curve. That is
Yes.
it. Yeah.
Okay, just taking a screenshot. Thank you, teacher.
All right. Do you have
Excuse me,
Hamida?
teacher.
Hamida, you have your hand up. Hamida.
Teacher, I was asking that are we going to draw even the cooling curve?
That is what I requested you to do. I said you are going to draw the heating curve, and then thereafter you also draw the cooling curve. So the cooling curve is the assignment. Otherwise, the heating curve I've given it to you, I've shown it to you, it is here. And also, if you went to the textbook, the prototype that we were using some time back, if you went to page 30, you'll find there that, but the cooling curve is not there. So I want you to generate the cooling curve.
Okay.
Right. And then Husna is, I saw your hand up, Husna.
Excuse me, teacher.
Is that Husna?
Yes, teacher.
Mm-hmm.
Teacher, like, I wanted to ask, like, can you briefly explain the cooling curve?
You want me to explain the cooling curve?
Yes.
Okay, now I will just give you the hint. I'll just give you the hint because that is part of the assignment. Now, when you start with the steam, we say the steam is at a very high temperature. So how do you turn it into water? You turn it into water by removing the heat from that steam, by cooling it. And there's different methods of cooling it. Of course, if you have, I don't expect you to talk about putting the steam in a refrigerator because it will spoil the refrigerator. And we can devise means of cooling that steam. When you cool it, the temperature is going to reduce until it reaches about 100 degrees centigrade. When it reaches 100, it will remain at 100 for some time until when all the steam has turned into water. Then, when you continue cooling that water which has been formed from steam, when you continue cooling that water, you will see the temperature dropping or reducing. The temperature will be reducing. It reaches a temperature of about 0 degrees centigrade. And when it reaches a temperature of 0 degrees centigrade, it will remain, the temperature will remain at 0 until all the water has become ice. Now, when all the water has turned into ice, then if you continue cooling, the temperature is going to reduce further. But of course, in the laboratory, we cannot have, we don't have facilities to reduce the temperature to as low as the 25, as indicated on this diagram. But possibly we can reduce it to a temperature of about -1, -2, -3. So it will be the reverse of this curve here. This is the heating curve. But the cooling curve will begin from a high temperature. So in between here, the steam will be cooling. In between B and A. Of course, I'm not saying that this is how the curve is going to look like. You have to think about, before you draw the curve, think about what is happening. We are saying start from a higher temperature, and since this one is representing the time, so you will start from time t. So time temperature will be very high. At 0 degrees centigrade, the temperature will be very high, that of ice, of steam. So it means when you have your axis like this, this is your temperature axis, that is your time axis. So it means
Guys, please mute yourselves.
0 degrees centigrade, the temperature should be maximum. When you are drawing the cooling curve, 0 degrees centigrade, the temperature should be maximum 100. Whereas when you are drawing a heating curve like this one, at 0 degrees centigrade, the temperature is at its minimum.
And shukran, please.
Okay. So it means the cooling curve that I expect you to draw, you are going to start. Let me just give you a sketch of what I expect.
Teacher, I'm done.
Okay. So I will expect.
So we are done.
I will expect.
What is the spelling of latent?
I would expect the temperature to start from because this will be representing 0. So at 0, the temperature will be very high. As time goes on, the temperature reduces. So I want you to complete the curve from there. Somebody is asking the spelling of latent. Latent is L-A-T-E-N-T, like that. Latent. So in other words, we have two areas on this curve where latent heat is being used between B and C. That is at 0 degrees centigrade. We are heating the ice, but it is not. The temperature is not rising. That means we have latent heat, which is being added here. Okay, I said already that latent is a Latin word which means hidden. You are adding heat, but as if it is hidden, it is hiding somewhere. It is not being used to raise the temperature of the ice, because it is remaining at 0 degrees centigrade. The second point where latent heat is shown is between D and E. When the water begins to boil at 100, it will remain at 100 degrees centigrade until when all the water has turned into steam. That is when the temperature will start increasing. So if you are cooling, you are going to start with, this is your temperature curve, and this is your time curve. So at 0 degrees, or let me say at possibly minus 45 degrees centigrade, it will not be at 0 or near 0 as it is in the heating curve. So at 0, you will have the highest temperature. When I'm talking of 0, I'm talking of 0 time. Okay, at time t is equal to 0 minutes, the temperature is maximum, because we are talking about steam. So we are cooling steam. So at that temperature, when you start cooling it, the temperature reduces until it reaches another temperature at which the steam will be turning into liquid water. So at that time, the temperature will be remaining constant. And when you continue cooling, again, the temperature of the water will now drop until it reaches 0 degrees centigrade, when it remains also constant. Right, I think those are the questions that I will take, and possibly I can look at a few charts, but the problem is you are misusing the charts. I said at the beginning, you cannot serve two masters at the same time. Somebody is saying, the teacher, the part of ice, I never got it. Ice is solid, solid water. So I don't know which part you are talking of, because we said ice. Ice, when you cool the water, liquid water, until it reaches 0 degrees centigrade, that water will solidify. That solidification is what we call freezing. So it will freeze, and when it freezes, it forms ice. So in the previous discussion, we were talking of how does the ice behave or turn when you heat it? How does it turn to water and eventually to steam? We said when you heat the ice, possibly if it is at the temperature which is lower than 0 degrees centigrade, that temperature is going to start rising slowly until it reaches about 0 degrees centigrade. And when it reaches 0, it will not rise. Instead, it will remain constant. So it remains constant because the particles in the ice are being broken down. The forces holding them are being broken down so that it turns into liquid. So that's why the thermometer does not register any increase in temperature, despite the fact that you are heating, you are continuously applying the heat to the ice. So I hope that is okay. The problem is the charts are too many. From D to E, what is happening? That is a bubble. From D to E, if you are referring to this one here, from D to E, I hope that is what we are referring to. That one is water is boiling. The water is boiling. It has reached the boiling point over 100. So at that temperature, the heat which is added to the water does not increase its temperature, but instead it is used to break the forces that are holding the molecules in water, or they are what that are holding the molecules of water in the liquid state, so that when those forces are broken, then the water molecules will just disperse, will just join the vapor or the steam.
Thank you,
When you break those forces. Right, then how do they cool steam in tubs? I think I remember saying that we have several methods of doing this. Okay, you can if you have the ice cubes, you can get a sample of steam, and then you place it in the ice cubes, and then you observe how the temperature is reducing. But I don't expect you to put the steam directly into the refrigerator, because it can spoil it. But you can just get the ice cubes Now, if we are doing the experiment, for example, in at school, what we can do is we can get some water, and then we put there some salt, common salt, and then we put it in a fridge or a deep freezer. When that water cools, it will form ice at a temperature of less than 0 degrees centigrade.
Excuse me, teacher.
Just like when you are boiling water. If water starts boiling and then you get a crystals of sodium chloride, salt, and you add it to that water, it will stop boiling for some time, and then it will start boiling later on. So these are things that you should be able to even explain to your parents.
Excuse me, teacher.
Yes.
Can we find out that work in the cyber work?
What I showed you, the animation which I showed you is from the cyber.
Okay, teacher.
Excuse me, teacher.
Yes, please.
Excuse me, teacher. Teacher, at times you say that when you hold ice it's slippery, but at times when you hold it in your hands it's sticky.
It is?
Sticky.
Are you sure? Sticky in which sense? Unless the water was contaminated with something else. Otherwise, if it is pure water which has frozen, it will be slippery, not sticky.
Teacher.
Yeah? Yes.
Teacher, from the refrigerator, that's when it's sticky.
Say it again.
When it's from the refrigerator, when it's sticky.
No, it is not sticky. There's nothing like sticky. We said it becomes slippery. When you hold the ice, the ice is made from the water, it will be slippery, not sticky. Where are you getting the word sticky from?
Teacher, what I mean is that it freezes on your
Like
hands.
it's very stuck on the cup.
One person at a time.
Yeah, like when it's from the refrigerator, it's kind of sticky. Like even when you put on it. Okay, like from the fridge.
You are misusing the word sticky.
Teacher, do you think it happens to your skin when you get it from the refrigerator?
It is not sticky. It is slippery.
Yeah, like when you get it from the refrigerator.
It is sticky.
When you lick it.
It gets stuck on your tongue.
Now you see, you
Yeah.
are misinterpreting. You are misinterpreting the what we are discussing. We are talking of. Now you see. Okay. Now me, I'm not a fan of. I'm not a fan of the. You said what? Jolly jazz. Okay, I'm not a fan of those. So now you can see that people who are talking of sticky are not talking of the ice, but they are talking of the ice made of something different. We are talking of the ice which is made out of water.
Even the ice cubes can stick on the
Yeah,
tongue.
yes. Yeah, they stick on the tongue.
I'm even doing it right now.
I didn't talk about putting the ice on the tongue. I said when you hold the ice in your hands like this and you feel it, it will be slippery. Now for you, you are again bringing.
Teacher, when it's just from the fridge, it sticks on the hand.
I'm not talking about the
Yes,
tongue.
teacher, it sticks on the hand.
Yeah, on the hand, on the finger.
It's out of the fridge.
You are
when you've just got
now
it out of the fridge, it's sticky, and then I think after a while it becomes slippery.
Now that is what we are saying. Why does it become slippery? Leave alone the sticky, because when you have just got it from the fridge, the temperature of your body and the temperature of the ice are quite different, very different in fact. Your body temperature is at about 37 or 36 point something. the ice is at about 0. So you expect that the moment you hold it like this, the surface of the ice is going to start melting, and therefore that melting makes the ice cubes to become slippery.
Got it, teacher.
Okay. We are handing in the work. Where are we handing in the work? I was clear yesterday. I said, do the work in your when you are coming to school for the next term. You come with those books and we shall look at it.
Okay.
So do the work.
Yes.
Okay. I think those are the ones.
Excuse me, teacher.
Yeah.
Teacher, can you put the paper we see?
Which paper now? This one here.
Yes.
That is a heating curve when we are heating the ice. What I wanted, or what I want, is the cooling curve for water.
So what does this stand for?
What does
this stand for?
No, B, A, B, C, D, E, F. Those are just letters representing
changes.
For example, I wanted to show you that between A and B, the ice or the water is in solid state. Then I wanted to show you that between B and C, there is ice and water coexisting because the ice is turning into water. And then between C and D, we have only water. And then between D and E, we have water into steam. And then between E and F, we have only steam. That is what I wanted to show.
Has this lesson been recorded?
Can we get this lesson in the same?
People are not obeying the rules of class. Now, if we want to listen to each other, when one is talking, another one listens. If all of you are talking, then it becomes noise. Now, you see, as Amal is saying, teacher, please explain what latent heat of diffusion. I have not talked about I said latent heat of diffusion.
I can't hear you.
I'm talking about what the chart which Amal has shown me, has given on the screen. It is talking about diffusion, but I talked about fusion, not diffusion. I talked about when the solid state is turning to liquid state, or when ice is turning to water. The amount of heat that we are supplying to it is latent heat of fusion, not diffusion.
Is it with 2 A's?
I just want to take a picture of this work I'm sending. They have a laptop here. Yeah, when they got gold.
Talking quiet, it's me talking. Teacher, fusion, is it with 2 A's? To the word fusion, is it with 2 A's or 1 A's?
There is a difference between fusion and diffusion. I talked about diffusion, but I did not talk about diffusion. I said latent heat of fusion, F-U-I-O-N. But I did not talk about diffusion. Don't misinterpret what I said. I said
so with 1 A.
Latent heat of fusion, not diffusion.
But fusion has two A's.
Fusion has?
Two A's. Two S's, like two A's. A's, double.
There's a difference between fusing and I think you could be talking of fusion. Fusion is different. I'm talking of fusion. From the word to fuse, F-U-S-E, to fuse.
Okay, thank you, teacher.
Yes.
Excuse me, teacher, can you please repeat for me the meaning of the of a boiling point?
Say it again.
Teacher, can you please define for me the meaning of boiling point?
What is wrong about the boiling point? Did you hear what she said? Right. There is no point of boiling. We said when the ice is turning into water, we say the ice is melting. And at the temperature, when the ice is turning to water, the temperature will remain constant at 0, for example. When ice is turning to water, that remains constant at 0. So we said the heat which you are supplying is the latent heat of fusion. Okay. Then this one here, between D and E, since we are supplying heat to the water, but the temperature is constant at 100, then we refer to this one here, we are supplying here as the latent heat of vaporization. So latent heat of fusion here, latent heat of vaporization there. So teacher, on the cooling curve, does the ice part be in negatives? Ice will freeze at 0, but you can also freeze it beyond 0. That means it is possible to freeze water and forms ice, which is at minus water and forms ice. It is possible. But what is important is that as it reaches 0 degree centigrade, it freezes and becomes ice. I wrote the holiday work on foolscaps. Is it okay? Oh, I wrote it. This one I answered. I said write it in the notebook because I lose them. People are thinking of recorded lessons simply because you are making use, you are misusing the time instead of listening and writing things which are not coordinated. Okay. Don't rely on the recorded lesson. Just be attentive in class, and when there's something that you don't follow, let us know, because we have allowed you to ask the questions. I think this one who is saying, teacher, please mute us because some are not able to mute themselves. I think that one is very correct. So that's what we shall continue to do if people are misbehaving. So the assignment that I have given is for you to draw two things. One, you draw the heating curve, which is here. The heating curve. When you have drawn it, I want you to indicate. You show a key. In the key, you show that between A and B is solid or ice. Between B and C, ice is turning into water. Between C and D, this is water. And between B and E, water is turning into steam. And between E and F, that is steam. So here, the ice is increasing, is warming up. Between A and B, you have the solid ice is warming up. Between C and D, you have water warming up. Between E and F, you have ice. I mean, you have steam increasing in temperature. Then between D and E, it's boiling at 100 degrees centigrade. Between B and C, the ice is melting. So even when you are drawing the cooling curve, so this is the heating curve. When you are drawing the cooling curve, I want you to also indicate a key which is showing you what is happening here, what is happening here, what is happening here, what is happening there and there. But of course, the cooling curve will not be the same as this one here. The shape will be different. Okay. So we shall end at that, and I hope when we meet next, you have done the assignment. So have a nice afternoon.
Bye, teacher.
Goodbye.
Excuse me, teacher.
I think it is a nice week and not a nice afternoon.
Teacher, thank you for the lesson. Bye, Joseph.
Thank you. Bye-bye.
I have a question.
Bye, teacher.
I have a question. I have a question. Teacher, is who a darling?
Bye, Patricia. Bye, Joyce. Bye, Favor. Bye, Zoe. Bye, Clara.
Bye, all centralized.
Drop what?
Bye, all NSM actors.
Hey, Central what? Central what meets you.
Bye, teacher.
Bye, Melissa Milk.
Go back now.
Kagwa. Kagwa Joeria.
Bye, Rolita.
Bye-bye.
Bye, Leila.
Rolita, how come you're the host?
Bye, Amisa.
Leila.
Saying bye. Just request for me. God knows.
Phosphor.
That who said that in the school. That who said that. Kale ziligenda wera mwenda kitundu. Hi Sheila.
Does it like it's not like